Recording has started.
So we left off last Friday. We were graphing using tables and plotting points. And I had left you with a worksheet. And on that worksheet, there were 10 equations we needed to graph. Now, the first one we had already done together. Y equals 3x minus 2. You plotted that one out, you got a line like that. The second equation, y equals 6 minus x. Would look something like this when you graphed it. So another line, just sloped differently across the graph. Number 3 gets a little more interesting. Y equals x squared plus 2x plus 1. Obviously, this is not going to be a line. When we go to graph this one, we end up getting a parabola, something like that. Number 4. Y equals the square root of x plus 6. Now this one is a little unique compared to the ones we've done here so far. You'll notice the first 3 all had arrows, a little bit sloppy in cases, on both ends of the curve. That meant it could continue going on in either direction forever. This one here, number 4, only has the arrow at the end, one end of the curve, not at this end over here. Well, why isn't there an arrow at that end of the curve? Well, because if x is negative 6, we hit a limit. I put negative 6 in for x. Negative 6 plus 6 is 0. Square root of 0 is 0. That's just fine. But if x is anything smaller than negative 6, let's say if x is negative 7, negative 7 plus 6 is negative 1. We try to take the square root of negative 1, we get an error. So x cannot be smaller than negative 6. Even negative 6.1 would cause an error because we'd be trying to take the square root of a negative. So this graph cannot continue in that one direction. It can only go off on the right side. If this were an associate degree technical math course or an intermediate algebra or college algebra course, we'd talk about the domain and range of functions. That would be a limit on the domain of a function. Let's see what equation number 5 looked like. It was y equals 3 plus 3x. Looks something like that. So it's back to being a line. Question number 6 was y equals 2 to the power of x. Gives us a curve, something like that. Couple of things here. One is, once this gets past 0 here and we're moving into x being positive, it takes off rather quickly. It's called an exponential curve. We don't deal with exponentials in your program, but the only program we had that dealt with exponentials was the telecommunications program because their circuitry had a lot of exponentially modeled circuitry. The other thing we notice here is as we move to the left, we get closer and closer to the x-axis, but we'll never touch it. That's called an asymptote. It's a line on the graph where our graph of our equation gets closer to that line. It approaches it, but never quite reaches it. Number 7. Y equals x to the third minus 1. Up with a curve, something like that. Called the cubic curve. Number 8 can be pretty tough to graph. Y equals 8 over x. I suggested some numbers for x there. But if you tried to use the 0, it didn't work out. This ends up being actually 2 separate curves, one there and one like that, because x can never equal 0. So there's actually 2 asymptotes here. There's one right here because x can't equal 0, but the graph from either side will get closer and closer and closer to that, just never actually touching it. Same over here. There's a second asymptote, which is the x-axis. Same thing's going to happen here. This is going to get closer and closer and closer, but never touch it. Same over here. Number 9. The equation was y equals 4x squared minus 8. We end up with a really sharp, narrow parabola. Like that. And finally, number 10. Y equals 3/4 x minus 4. We get a line like that. So the first thing I want to explore here is the 4 equations that form lines on the graph. Those 4, 1, 2, 5, and 10, formed lines on the graph. If you got any of your others formed lines, you missed something when you were plotting points. You need to go back and plot more points and see where they deviate from being a perfect line. If we look at the equations for the ones I have highlighted in green compared to the others, there are some things that the ones that are not highlighted have that those in green do not have that make those not be lines. You'll notice the green highlighted ones are all fairly simple equations. The other ones are a little bit more complex in different ways. One of the things that they have there we have x squared, x to the third, x squared. They have powers on the variables other than 1. I mean, technically y equals x has a power on the variable. It's just x to the power of 1 and y to the power of 1. Now this one right here, we're going to throw in the same category. We talked about exponents, including both powers and roots. That gets included with these powers. So the variables inside a square root is the same as having a power on it other than 1. Going back up here, this one. Here, the variable x is the power, 2 to the power of x. Excuse me. So we can't have a variable in the power either. And the final thing we can't have is right here. We're divided by x. 8 divided by x. We cannot divide by a variable. So if our equation has any of those things, then it is not linear. In other words, it will not form a line on the graph. So an equation like this, y equals 3x plus 2 to the third power. At first, it looks bad because of the third power, but that third power is just on a number. This is really just y equals 3x plus 2 to the third power is 8. So that's fine. That will be a line. Y equals 5 divided by x. Well, we're dividing by the variable. That we can't have. Y equals 2 over x. Well, once again, it's a different form, but we're dividing by the variable. It's 2 divided by x. Will not form a line. So here it looks like the x appears twice, but we can combine that. Y equals 3x minus 3. That's going to be just fine. That's going to form a line. Y equals 7x plus x to the third. Oh, we have a power on our variable other than 1, so that one's not going to be a line. Y equals 5x minus the square root of 49. Well, that's just y equals 5x minus 7. The square root of 49 is 7. Well, that's fine. Even though it's got a square root in it, it's not on the variable. Y equals 3 to the power of x. Well, there our variable is the power. That's going to be a problem. That will not form a line. So once we've got to where we can look at an equation and see whether it's going to form a line or not on the graph, there's some shortcuts we can take. So let's start out by looking at the simplest forms of linear equations we can come up with. I'm going to start out with just y equals x. So if y equals x is our equation, make a little bit of a table here. If x is -3, y is just -3. So that's a dot right there. If x is 0, y would just be 0. That's a dot at the origin there. If x were 3, y would be 3. Dot right there. That gives us a line going corner to corner across our graph through the origin. Something like that. Now, y equals x is a pretty boring equation. It's about as simple as we can get. So let's look at things we can do to make the equation more complicated. For example, we might do y equals x plus 2. Well, now if x is -3, -3 plus 2 is -1. That's a point right there. If x is 0, 0 plus 2 is 2. That's a point right there. And I crowded myself here, but if x is 3, 3 plus 2 would be 5. 3, 5 is going to be right there. We end up with a line that goes the same angle across the graph as that original line. See, the only difference is it's moved up 2 spots. So, makes sense if we tried y equals x minus 3, it might be predictable in the other direction. If x is -3, well, -3 minus 3 would be -6. That would be right there. -3, -6. If x were 0, y would be 0 minus 3 would be -3. Be right there. If x were 3, 3 minus 3 would be 0. That would be right there. So you get that green line. Again, it's the same angle across the graph as that original black line. It's been moved down 3 spaces. So adding or subtracting to our equation just moves it up and down on the graph. What if I try y equals 2x? Well, if x is -3, 2 times -3 is -6. That's a point right here. If x is 0, 2 times 0 is still 0. That's at the origin, 0, 0. If x is 3, 2 times 3 is 6. So 3, 6 would be right there. So I get a line like that. It goes through the origin again, but it's steeper now instead of 45-degree angle like the others were. So if we multiply the variable, it makes our line steeper. Let's try dividing it. And rather than dividing it, I'm going to do this. Y equals 1/3 x. Multiplying by 1/3 divided by 3 do the same thing. So now if x is -3, 1/3 times -3 is a -1. So -3, -1 would be right there. If x were 0, 0 times 1/3 times 0 is just 0. If x were +3, 1/3 times 3 is just 1. So we've got a flatter line across the graph. Now, the only thing we don't have so far right now, all these lines as we go left to right go up. Let's try y equals -2x. So now if x were negative 3, negative 2 times negative 3 would be a positive 6. Instead of negative 3, positive 6 like that. If x were 0, negative 2 times 0 is just 0. If x were positive 3, negative 2 times positive 3 would be negative 6. Like something like this. So there we get our line going the other way across the graph. So there's only two things that can happen to our graph. We can add or subtract from it, which moves it up and down. So instead of going through the origin, the minus 3 here means we go down 1, 2, 3. So our graph starts right there, 3 units down from the origin. That's referred to as the y-intercept. Because that's where it intercepts the y-axis. Remember, this is the y-axis here, vertical axis. The number multiplying x then tells us that this is not going to be a 45-degree angle across the graph. It's going to be a little steeper. Be something like that. That concept is referred to as the slope. And it's actually a ratio of rise to run. Now, 2 doesn't look like a ratio. It looks like just a whole number. We make it into a ratio, or a fraction, if you prefer to call it that, by putting it over 1. It's 2 over 1. So that's saying is from that starting point, from that y-intercept that we had here, we rise 2, we run 1. There's the second point on the graph, on the line. So then I have y equals 2/3 x plus 2. The plus 2 is saying from the origin, we go up 2. That's where we're going to start this graph. The 2/3 multiplying x. Well, remember the top number, the numerator is the rise. The denominator is the run. So from that first point, this one right here, we're going to rise 2, run 3. That gives us our second point on the line. Our line goes through those 2 points like that. We might have y equals negative 1/2 x plus 3. So again, the number out here by itself is where we start. Start at plus 3. So go 1, 2, 3. That's right there. That's going to be the starting point for that graph. The negative 1/2 slope. The negative, positive or negative, goes with the rise. The run is always left to right. So this is a negative slope, so that means we're going to go down 1, then run 2 to get to our second point. So the run is always left to right. It's the rise that's either positive or negative, up or down. So y equals 2x minus 2. We start out at minus 2. That's our y-intercept there. The 2 multiplying x, remember, has to be a fraction. It has to be a ratio, rise to run. So we make it 2 over 1. So from this starting point that we found, the y-intercept, we rise 2, run 1 to get our second point right there. Now, if that's not enough information for us to feel comfortable graphing, we can do our slope again. We can rise 2, run 1, make another point. We can keep going if we needed to. There's our line. It doesn't say that simple. Often we have to modify our equation to put it into the form where we know how to graph it. For example, it could look like this. This is not in that y equals form. All of these were y equals. We call that graphing form or slope-intercept form. This is y plus 2 equals. So to get it to where we can graph it, we have to get y by itself. 2 has been added to y, so we're going to get rid of it by subtracting. Now remember, when we add or subtract, we can only combine with things that have the same name. So that means I only combine it with one digit on each side. I subtract the 2 here, makes that 2 go away. On the right side, I have to subtract 2 1s from the 1 1. So I have 1 equals the 3 over 2. X isn't going to change, but positive 1 minus 2 is a negative 1. Now I start out here at negative 1. That's my first point. Then I have my slope of 3 over 2, so I'm going to rise 3 and run 2. There's my second point. And draw my line through those points. I might have 3y equals 2x plus 6. Here I've got the 3 with the y that I need to get rid of. 3 is multiplying y. I have to get rid of it by dividing. So I'm going to divide by 3 to make that go away. When we multiply or divide, we do not need the same name. That means every digit can be multiplied or divided. So on the left side, we divided the 3y to get rid of the 3. On the right side over here, we have both the 2x and the positive 6. Both of those need to get divided by 3. Do the 2x divided by 3. We just treat it as a fraction. 2x divided by 3 becomes 2 divided by 3x. 2 divided by 3 is just going to be 2/3. Then we have the x there. So since the 2 divided by 3 doesn't divide out evenly, we just turn it into a fraction. It's 2 over 3. Then we have the 6 divided by 3, which is a positive 2. So when we go to graph this, we start out at positive 2. Right there. And then from there, we rise to run 3. There's our second point. A line goes through those points like that. We're going to give you some homework to work on in the big book. Page 464, 465, exercise 16.2. Page 466, exercise 16.3, and page 467, Exercise 16.4. We'll start out with those. Tomorrow we'll pick up from there, talking more about this slope-intercept graphing. And then we'll work ahead from there. Let you guys have the last 16, 17 minutes here to get started on your homework if you like. I'll be on the network if you have any questions. Otherwise, if you prefer